So thank you all for coming. Actually, I'm very sorry to the students for depriving you of pizza and sandwiches and all the usual stuff that comes on student colloquium. So hopefully this will make up. But I'm happy to have Susobhan visiting us today. Susobhan is a PhD student at NISER Bhubaneswar. He works with Algorithmica. He's worked on graph-related problems from a parameterized complexity. He's also looked at fair division, and he'll be talking about some mix of his work in this talk today.
Thank you. So I started working on graph problems, and since most of the graph problems, I mean the graph subset, finding subset problems, these are hard. So take a look at it from approximation, randomization, and many other point of view to deal with the hardness. There is another notion called parameterized algorithm. So here I will be talking about parameterized algorithm for different graph problems. And mostly those graph problems you can broadly categorize as either connectivity problems or graph partitioning problems. So before starting, let us just go over once what fixed parameter tractability is. So given a problem and a parameter k, if there exists one algorithm which runs in some polynomial in the input size, but it can be exponent in the parameter size, then we say this kind of algorithms as a fixed parameter tractable algorithm with respect to that parameter k. There is another notion called XP. So before checking fixed parameter tractability of one problem, we check whether the problem is XP or not. So by XP, I mean there exists one algorithm which runs in n to the f of k for some parameter. Okay, so this is the overall picture for the when you look at fixed parameter tractability for one problem. First, we ask for one parameter whether the problem is XP or not. If the problem is XP, then we look for
what does X stand for?
Exponential something. I don't know the exact slice wise. Yeah. Sure.
Why is X slice wise?
Slice this way. Okay. So if the problem is XP, then we become more ambitious and look for whether this is APT for this problem for the parameter or not. If not, then we try to look for some other meaningful parameter which is important for that problem. And if the problem is FPT, then again we are happy and we look for some other things which I will discuss later in the talk. But if not, then there is a notion similar to NP hardness here also, that is called W hardness. And again, we try to look for some other parameters, whether we can get FPT algorithm with respect to that parameter. Okay.
Can you go to the picture also?
So as I said earlier, that mostly I will be talking about problems which can be categorized as connectivity, graph connectivity, or graph partitioning problems. So broadly speaking, so in a connectivity problem, you are given a set of vertices or pair of vertices or a set of pairs, and you have to maintain some kind of connectivity between pairs or the given set. So with respect to some constraints, the constraints can be anything. So which will be disclosed in a moment when we look at specific problems. And in partitioning problem, the goal is to divide the vertex set of the edge set of the given graph. Sometimes we want to partition both with respect to some constraints. Okay.
What is the goal for connectivity again?
Connectivity?
Yes.
So maybe you can think of this problem, ST path. So given a pair of vertices, terminal pair S and T, you want to find connectivity between S and T. So what could be the shortest path between ST? What could be the longest path between ST? So this is one example of connectivity problem in general. So first connectivity problem I will be looking at talking about is AL path packing problem. Before going into the details of AL path packing problem, AL path packing is basically one variant of disjoint paths. So this is the I think the first problem we should talk about when we talk about disjoint path problems. So here we are given a terminal pair S and T and given a graph. We want to find whether there exists k many vertex disjoint path between that pair S and T. So let's say this is the graph we are given, and these are the two terminal the terminal pair S and T, and k equals to 3. That means we want 3 disjoint paths between S and T, right? So what disjoint, I mean vertex disjoint.
This is NP hard.
No, but this is not. Yeah. So this is one instance, instance for this. So you have these 3 parts, and this is not NP hard because from Angel's theorem, this problem reduced to max flow, right?
If you make it edge disjoint,
That's just.
it is just
So there's S1 T1, S2 T2 was simplified.
but you have 2 pairs.
Yeah. The next problem I will be talking about matroid-based path problem. Here, instead of a pair of vertices, you are given a collection of sets, and you want to find or you want to maximize the number of paths which connects to different sets. Right? So look at this example. Here S1 is this, S2 is this, P is 2. That means I want too many. So K equals to 2. That means I want 2 vertex disjoint path between S1 and S2. Right? This is yes instance for this. We have one path, then another. And this is also known to be polynomial time solvable due to this effort. And there is another variant of disjoint path which is called A path problem. In A path problem, instead of multiple sets, we are given only one set of vertices, an integer k. I want to find whether there exist k vertex disjoint paths which starts at one vertex at A and ends at another vertex at A. So you can think of this as a special case of matroid-based path problem. Why I'm saying so? Because you can consider each of the vertex as a set, and you want to maximize the number of paths connecting those sets. So this is basically a special case of matroid-based path problem, and the polynomial time algorithm translates for this as well.
So the internal vertices can be from here? Or
No.
the path has to be entirely outside.
How many entirely outside?
Path has to be entirely outside.
Sorry?
Path has to be entirely outside.
Entirely outside. The starting and ending vertex should be outside.
And then I think it was.
Yeah. So this is
What does an A path mean? It has to be, the path has to be completely contained in A.
no. So the path should start and ends at it.
And to be completely in
Other vertices would be outside it.
All the other vertices except the terminal vertices should be outside it.
Oh, it's just the opposite.
Yes.
That is because what is inside it is break into 2 parts.
Can you remind me of better problem?
Oh,
PGM slide, can you go back? Yeah.
So here you are given sets of vertices S1 through SP, let's say, and I want to find k paths which starts at one vertex and one SI and ends at one vertex and one SJ.
And I and J can be the same also.
No. So here I and J is different for matroid-based path problem. So that is what I am saying. This problem is a special case because if you consider this, every vertex as a singleton set, the problem is a matroid-based path problem.
Yes.
But where was the constraint in the major problem that the vertices, the paths cannot go through their side or something? So here there is.
So you are saying that it can go through some.
Here the constraint, the paths cannot go through A, right? Except for the endpoints. So what is the corresponding thing in the majors?
Okay, so so at one point of time the path leaves one set SI, right? And why not you consider that vertex and the other vertex in the other set as the path?
Oh, okay. So if you have.
No, but
I mean, it can
I mean,
still be
if you, I
want.
mean, in the sense that if you are able to find k vertex disjoint paths
Yeah.
that pass through A, you might as well
just
short
drop
circuit
it.
and re-enter A for
Exactly.
the first time.
But what if the only way to connect the second vertex is through this one vertex?
No, but then you can't use that vertex again anyway, so you
Yeah.
call that your path.
So call that your path.
Vertex disjoint paths. No?
They have to be vertex disjoint, which means that vertex you could not have used again.
And so you are saying about this, let's say we have one.
And you're saying the short circuiting thing doesn't work, right? Because we
Not short circuiting, in the sense that drop the path after you re-enter the set A.
You redefine your solution.
Let's say your path was this.
Yeah.
Right?
Yeah.
It contains two vertices, V1
Sure.
and V2.
Yeah.
Here, let's say V.
You just
Some-
consider V2 VK.
Yeah. So
Yeah.
why don't we consider that this path only, the subpath joining V2 and VK?
Take a minimal path that.
Minimal path. So is it clear?
No, but anyway, to find it, let's keep going and come back to this.
Okay. Uh, yeah, A path packing problem is good. So almost a decade back, Golubas and Thilopos studied.
So, and these k different paths, not from the same pair, right? When if one is from S1 to S3, one is from S2 to S3.
Yes. So Golubas and Thilopos introduced.
Sorry, one minute. It definitely can't be on the same pair because then they are not vertex disjoint.
No, same pair.
Not required on the k.
And also the front and the end, I don't think they count.
Yeah, front and the end.
Like the
So
first
the
one
front
and the
one
last one did not count. We can have many parts like this.
Oh, okay.
Okay. Then that's
That is also allowed. Yeah.
I see.
So only the internal vertices that
Internal.
which okay. Anyway, the vertex disjoint from the
I see. So one set could just have one vertex.
Yes.
The rest would have 10 vertices.
Yes.
And you would say that there are 10 edge
Okay.
disjoint paths or sorry, 10 vertex disjoint paths existing between these two sets.
For matroid-based problem, I don't say this because here you have, once you have one vertex here, the paths won't be vertex disjoint. So here I am not considering internally vertex disjoint.
Oh, what is?
Okay, no.
Yeah.
So then I don't understand. But anyway, let's keep.
No, then I was wrong. I think he counts the start and the end.
No, but in the usual vertex disjoint paths you don't.
Yeah, they usually don't. Yeah.
Yeah, so I didn't get the question.
So-
actually.
So in the A packing path also, there also it's like internal disjoint. In the A,
Those are completely vertex disjoint.
those are completely.
So there is at most one vertex disjoint path from S to T.
There can be.
At most one vertex disjoint path from S to T. No, S is small s.
No, you just disturb the.
I mean, what he said is that
All the k
has to have at
are all
least
disjoint.
k. If you're looking for k vertex disjoint path, every subset has to have at least k vertices, right? Otherwise, anyway, you won't have.
For Magnus,
Because 8 points count.
you could take multiple pairs of sets.
Okay, here's a question. There is a complete bipartite graph.
Yes.
3 vertices here, 3 vertices here. What is the number of vertex disjoint paths?
3.
Three.
Matching.
Yeah.
Okay. So
So you
Then
can't
it's not-
have more than.
it's not 9 then.
Yeah, it's not 9.
Okay.
So it's not internally vertex disjoint.
Because endpoints are also being looked at.
Yeah.
Yes.
Unlike the usual ST.
ST path, yeah. For ST path, you are the like you can think of the classical disjoint path problem where you are given pair SITIs and you want to connect those SITIs through a path. So here you can guess the pairs which you want to connect and then you can solve the disjoint path problem. Yeah. So they introduced a version of disjoint ST path problem with length constraint. So what do I mean by length constraint? So they want the path, the length of each path should be bounded by L. It's not, I don't want any arbitrary length path. And the moment I incorporate the length constraint, the problem becomes hard. So earlier it was easy, but now it is hard. And motivated by this length constraint, Belmonte et al. They have introduced length constraint in the A path packing problem as well. And no, with length constraint, we call this problem AL path packing problem. So here you are given a set A and an integer two integers k and l, you want k vertex disjoint A paths, each of length exactly n. Yeah. So for
So now this argument will not apply.
no,
Okay.
Because of exactly being.
exactly yes, you are not allowed to like take any subpath.
Okay.
So for k equals to 2 and l equals to 3, this is no instance clearly because we have only one path of length 3. We don't have two disjoint paths. And though earlier it was yes instance when only k equals to 2.
Wait, what are you saying? Of course, you have these two paths around the sides, right?
Which one? A paths. So I want a path. So the moment I consider this path, how do I reach this using two hop?
So A path means that it is not allowed to touch it.
The intermediate.
Intermediate is allowed.
Yeah.
Outside.
No,
So-
that is completely.
Why don't I just take the outer shell?
Yeah, this one.
Those three and these three.
He's counting the number of vertices.
Oh, that's length 4. Oh, acha. Oh, okay.
What?
Acha.
Number of birds. Oh, number of birds. This is 4. Okay. It's become okay.
So when you use the length path,
Because usually.
so
Length of a path is also counting the number of vertices.
Yeah, there are notions where considered as the edge length. There are notions where it considered as the length of the number of vertices in that path.
It doesn't matter, right? Just one.
One after.
Yeah, in generally we denote P3 as paths on 3 vertices. That is the normal notation we use to denote paths on 3 vertices, the P3, P4.
Can you just go back? So this exactly is it a new constraint or was that a constraint in the previous thing also?
Yeah, they have introduced this.
At most then.
No, so they have introduced both, at most and exactly.
And both are hard. For the ST
Yeah,
constraint.
yeah. Yeah. And since the problems are hard problems, so they have considered parameterized complexity. And when you introduce parameterized complexity, the natural parameters are those which are given as inputs, like K, L, A, the size of the A. But parameterized by all this, there is no FPT algorithm that they have showed. But when you combine parameters like this, K plus L or A plus L, the problem becomes FPT. So this more or less like is an end of story for all those natural parameters. So there are another category of parameters which are called structural parameters. So which we how the graph look like. So that is depending on those structural parameters. So they parameterize by path width of the graph. So even if you don't know what path width of the graph is, so no need to bother. So path width you can think of as a quantity which somehow characterize how the graph looks like.
K is at most size of A, right? So what is why are we mentioning both?
What K
Is at most size of A, right?
K is at most.
I can't
yeah,
have more.
yeah. But A can be very large quantity.
Okay, fine.
Yeah, but I think the point is that if there is an FPT with K plus L, there's obviously an FPT with A plus.
Yeah, true. So this result actually translate to this.
So no,
Yeah. So now the situation is like this. So tree width is a smaller parameter than path width. That's why any hardness result on path width will translate to tree width as well. Okay. Now the question is how to find a new parameter for which the problem is hard. So when we show the hardness result or when we show the FPT result, so for FPT result we want to find the smallest parameter for which we can show FPT result so that we can restrict ourselves much. And for hardness result we want to find the largest parameter for which we can show the problem is hard. So this is where is the theme of this paper, this one. And we showed that this problem is unlikely to be FPT for this parameter, distance to path. This is basically the number of vertices you need to delete from a graph so that the resultant graph is a path. So this is a very large parameter, it is clear. If you are given a dense graph, you have to delete a lot of vertices.
So you want one path, like.
Yeah, only one path. So the resultant graph is a path. Okay. So the moment I prove that the model is hard for this, it also translate the result for this DLF, that is disjoint linear forest, that is collection of disjoint paths, and any acyclic graph, distance to any acyclic graph.
What is FPS?
That is fit by vertex set. That means you want to delete those.
So this DTP is also NP hard to compute.
Yes.
Okay.
And
But all of these.
Wait, is it DTP? Oh yeah, it's the longest path.
Yeah. So I guess all of these are NP hard to compute, DTP, DLF, DWT.
yes, yes. Yeah. So the moment we prove this, this is more or less the end of the story in that direction, which can be compared with DTP. So we had to look after another parameter which is not comparable with DTP. So we looked at APS, CVD, and we proved that the problem is FPT parameterized by CVD. Again, as CVD is a smaller parameter than vertex cover, CVD is cluster vertex deletion number.
What is it? Cluster what?
Cluster vertex deletion number. So so number of vertices you need to delete so that the resultant graph is a collection of disjoint links. Okay.
Number of vertices you need to do. Okay.
Yes. So vertex cover is a larger parameter than this because vertex cover, if you delete the vertex cover from the graph, then it is cliques of size 1. You have a collection of cliques of size 1. But to complement this result, we have shown polynomial kernel for the vertex cover. Now the question, what is kernel? The kernel is when given a problem, FPT problem instance, you
mean polynomial kernel for vertex cover or for the CVD problem?
Yeah, vertex cover.
Okay.
So the kernel is a polynomial time algorithm which you apply to pre-process your input instance, so that your resultant instance, the size of your resultant instance is now is bounded by some function of your parameter. And if the bound is on polynomial on the parameters, then we say the resultant instance is a polynomial kernel of the given. Right? So we get polynomial kernel for the vertex cover, but these are the gray zones. We don't know what are the in between parameters for which the problem is FPT, and here for which the problem is hard or FPT.
I'm sorry, how do the parameters in the blue line compare with the parameters you're picking in the red line?
Red line? Okay, so I don't know exactly where it lies with respect to parameter, but I know that there might be some parameter which is comparable with CVD.
But do we know how cluster vertex deletion compares to tree?
So I don't know. So those are basically incomparable. So
do you not know, or are they incomparable in the sense?
CVD with tree width, they are incomparable.
Okay, good. And this, sorry, just go ahead. Like this first red box that you have.
Yeah.
Like there's no label on it. In the sense that you're not sure what it is.
Yeah.
Something.
Yeah.
Which is comparable.
So that is what.
One such thing is minimum of the two.
The minimum.
Yeah.
So in general, isn't it the case that once you know that under a certain parameter, you have under this parameter it's an FPT thing, you automatically have a kernel for that.
Yeah.
This is an equivalent statement.
Yeah, the kernel is guaranteed, but the size of the kernel is not guaranteed. It can be of exponential size. So the goal is to how good kernel you can get.
So for example, we know of it, the first parameterized algorithm typically that people look at is vertex cover.
Yes.
So prior to this, was it known that vertex cover has a polysize kernel?
No.
Okay.
Wait, have you defined a kernel?
He mentioned what.
Yeah. So I have not written here.
What is a kernel?
The kernel is a polynomial time algorithm you run on the input instance to pre-process the reduce the input instance, the size of the input instance. You might have a large instance, you run the algorithm, and the instance size becomes some function of your parameter.
I see. So from the n goes away.
Yeah.
Okay, got it.
And then you can afford to brute force on that.
Yes.
Got it.
Yes.
Got it. Got it. Got it.
So the polykernel, that box, I mean, so polykernel for this problem parameterized by vertex first?
Yes.
That's what
Yes.
Sorry, polykernel for this problem parameterized by vertex. Oh, sorry. It's not, yeah, okay. Okay.
And
I misunderstood.
the running time of this kernel process
Algorithm is polynomial.
in n without any dependence on k.
Yeah. So k dependence can be there, but
Poly.
it should be poly.
So is it? I see. So it's FPT. It's not XP.
No, but the size of the.
Not FPT. This is exactly polynomial. So k is also smaller than
I
n.
mean, typically these parameters are never going to be more than k. Sorry, more than
n.
n.
True.
So
Yeah.
yes.
But what is wrong with having an algorithm that is FPT? Like you have a parameter k, it runs in time 2 to the k times poly and
But then you can just maybe solve the problem and output like a trivial yes or no instance. Right?
yeah, maybe you can, but maybe
If you allow
Oh,
me to
yeah,
run in
actually,
FPT time,
Yeah,
they
I
can.
will just, and the problem is that
Yeah.
I will just solve the problem and output like a trivial constant size yes or no instance. Or something.
Yeah.
Sorry, I mean, sorry, the definition you gave, it may be the same thing,
Mhm.
but what I understand of a kernel is like, I mean, you should have a polynomial time algorithm,
Mhm.
but the output of that algorithm is a reduced graph
Right.
whose size is polynomial in your parameter k
Yes.
and has no dependence on a. n.
Yes. Yes.
Right?
Yes.
Not
Absolutely.
is it polynomial?
Yeah.
Polynomial.
It's
There is
not-
polynomial.
It's not the polynomial code.
For polynomial kernel, it is bounded by
Right.
polynomials.
And the kernel is also specific to your problem and the parameter.
Yeah.
But as I said, that I don't know what are the smaller parameters. That is CVD plus the size of the A. But clearly, CVD is smaller parameter than this. So I don't know what's the status for the status of this problem parameterized by CVD only.
So, I mean, you have a plus a in many of these. Right?
Yes.
So you're saying now if you can remove the plus a from the.
Yes. 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 So there is an open question by Belmonte et al., which we could not also resolve. That what is the status parameterized by click width of the graph plus L?
was click width in the picture somewhere? In the previous picture?
Where was click width?
What is click width?
The click width has it has a recursive definition, but you can think of vaguely as how far this graph from being a click.
Being union clicks, I guess.
No, click. So it's like tree width. You want to
Union of clicks is like cluster vertex.
delete.
Sorry. Okay.
So it's like tree width, but now the bags have
Bag-
form a click.
No.
No.
The decomposition should instead be a.
Yeah, click
Okay,
decomposition.
Yeah.
Yeah. So the next problem which I will be talking about, which basically somehow
Wait, so here your result was turtle polytime in vertex 7.
yeah.
Okay.
Uh,
Everything else was prior work. The result was the
No, no.
polytime.
so
And
this is
CVD.
our result. So all three I have noted down here are
Okay.
our results.
I see.
Let me just see that again. So, what are the results?
So
in the CVD.
FPT for CVD, hardness for DTP, and polykernel.
CVD plus a.
CVD plus A.
CVD plus CVD.
Yeah.
And hardness for
But why did the polynomial kernel become BC plus? Oh, because then the brute force will be on A also.
Yeah.
yeah.
But A could be polynomial in N, so how does the kernel even work?
So for this one,
Yeah.
actually, when you vertex cover, you know the graph is independent set and your path must interact every alternate vertex to the vertex cover.
Mhm.
So you have a very restricted structure on it, and you can exploit the structure to bound.
The size of it.
Yeah.
As a function of it. Okay.
Yeah. The next problem is somehow you can connect the connectivity and partitioning. So before going into the problem, so let us look at this question. So given a graph, so can I say that for every pair of vertices, there exists a path. If you remove the set of vertices from that graph, the resultant graph is also a connected graph. This example. So is it true for this graph? For every pair of vertices, can I remove a path joining them so that the resultant graph is a connected graph?
Isn't this just, is it
This
just,
edge, right? This edge is creating the problem. If I remove this path, this is the unique path kind of.
is this the same as doubly connected?
No.
We're removing all.
That will be clear in the moment. So that is what exactly Lovaas conjectured. He conjectured that there exists one function f of k. For every f of k connected graph, there exists one path between every pair of vertices. If you remove that path, the resultant graph is a k connected graph.
What is f of k connected?
Yeah, that is what we don't know.
No, wait, go back to the definition. Where is k? Oh, I see it. Got it. Okay.
Yeah. So this conjecture is still conjecture. This has not been proved yet. But some of the cases has been proved.
Okay.
Like f of 1 equals to 3. What does that mean? So given a tri-connected graph, for every pair of vertices, you have one path. If you remove that path, then the resultant graph is a connected graph. For f of 2, f of 3, I know, but beyond that, there has not been much in the literature. But the interesting thing is,
So what would happen? Suppose you remove a path, and then one of the vertices on the path does not have any other edges. So would you count it as disconnected, or would you remove this
No.
vertex? And
So if there is one pendant vertex, if you remove that vertex,
it's not a pendant vertex. There's two edges, one here, one here.
so you were saying like this.
Yeah. So you remove this path. Now this vertex, is it isolated or is it just disregarded?
No, so if you remove this, but if this is adjacent to some other vertices,
It's not.
it's not. Then you have it's not
Delete the part, you delete all the vertices. Is that what you mean?
Yes.
Okay. So this should still be connected.
Yeah.
Okay. Got it.
You read the vertex. It's the induced subgraph on the remaining.
Yeah. Yes. So Kawarabashi et al. Proved a weaker version of this conjecture. They proved that there exists function f for which f of k connected for every pair of vertices. If you remove the edges of the graph, and the path should be induced here, not any path. The path is induced path. And if you remove the edges of the path, then the resultant graph is k connected.
What is this function? There are bounds.
They showed that this is f of k for general k.
What is the induced path?
Induced path as in
There are no other edges.
no other edges incident. So if you look at the paths, if you look at the vertices and the induced graph on those vertices, that will be a path.
Oh, regardless of parts.
Yeah. So
Sorry, wait, sorry, just go back. Okay, connected. Okay.
And the edge deletion and the vertex deletion things are like these are no bearing on the vertex deletion. Like, there is no implication towards.
edge deletion.
I mean, yeah.
Edge deletion is
Given this statement, there are no consequences to the vertex.
no. Because edge deletion is much more restricted case. The vertex deletion is more generalized.
So edge deletion is,
I think.
it's easier to connect it.
Right.
It's going, when you delete a vertex, you delete a lot more.
A lot, yes. Yes, that is what I said, that the weaker version of this method. So, motivated by this, we tried to solve this computational part.
I don't understand something. So, like, this go back to that slide. So, if it's FK connected, I mean,
So
it should be a monotone property in the edges, no? I mean, because from what you're saying, it is not. I mean, if you add,
F of k is larger than.
no, because suppose you add now edges to the graphs, yeah, and it need not be an induced path then anymore, right? Because he's saying it has
So
to be
that part
induced.
will not be an induced path. They will
Yeah,
have to be-
because then it no,
I mean, but there may be another induced path.
no, I'm saying if a graph
Yeah,
is FK connected,
yeah,
then by adding edges, the FK connectivity
Yes.
should not break down, right?
yes,
But it might.
No, but you're asking for more also, right? You're asking for the remaining graph to be K connected. So if you're going to increase your.
No, but if I don't have an induced path,
So he's worrying about induced paths. Do they still exist induced paths? I'm saying if
If
there is
there is
a path, you can take a shortcut.
sorry.
So we tried to solve this computational aspect of this problem. So here we want to solve a specific case given a graph and a pair. I want to check whether for this pair this condition holds or not. And also I want to add one more constraint, that is I want to bound the length of the path as k. Okay. So given S and T and k equals to 1, this is not an yes instance because there is no ST path of length k. But when k equals to 2, we have this path. And if we remove the vertices of those path of this path, then we have this graph, which is a connected graph.
So, okay, so now you are looking at a fixed set of two vertices.
Yes.
You identify two vertices and you
Yes.
want to know if there's a path of length K that is connected.
Yes. If I can solve this for S and T, then I can choose any pair and check whether which pair it falls. It fails that there doesn't exist any path.
Okay,
Now there is another version where no terminal is given. You are basically finding whether there exists any such path between any pair. Here you have for k equals to 1 in the earlier case when terminal pairs are given, that was no instance, but here it is yes instance. If you remove that, then you have this blue component.
sorry, I didn't understand this. When ST are not part of the input, then you.
Yeah. So in the
Are
earlier,
you asking, do they exist any pair of vertices?
yeah.
Why can't you just iterate over all pairs of vertices?
Yeah,
Why can't you just iterate over all pairs of vertices?
I can do.
Okay,
So that is what I am saying as the terminal independent version of those.
okay.
Yeah. So I'm just want an existential result, whether there exists one such path.
Okay.
And there is another edge version of this problem where I want to remove not the vertices of the paths, but edges of the paths. Here, for t equals to 2, earlier it was this path was giving me an yes answer. But here, if you remove that path, then this vertex will be isolated in the resultant graph.
Shouldn't the answer always just be an edge now? Or your terminal independent thing?
Terminal independent thing? No. No, because the first example you considered is there the edge is a bridge.
Okay, no, I'm saying, if you're saying that, I mean, but terminal independent thing, you can choose your terminals, right?
Yes.
So don't choose them to be the bridge.
Oh, okay. Yeah. For terminal independence, for any graph. But for you want the length to be k.
You said that.
Yeah.
It was at most in the previous slide also.
I don't know what that was in the previous slide also.
Yeah. It was at most.
But you want at most or do you want exactly?
I want that most. Yeah.
Okay.
No, I want exactly. Sorry for that.
Okay.
I want exactly. Yeah. But this is the yes answer when k equals to 2.
So, what is the yes answer? So
The black edges.
The black edges are.
Dropped.
Yeah.
The black edges are dropped.
Yeah, mostly can't be also the black edges. So which are the black edges?
This one and this one.
Okay. Yes. Okay.
You could have dropped this one also, right?
No, the edges I am dropping. So you are saying this one?
Yes.
But then this vertex will be isolated.
So I'm a little confused. So when we are removing a path, we are not removing all the vertices.
No, I am removing the edges.
Oh, now we are removing all the edges.
But without the vertices.
But you could take this top edge and then this edge, right?
Yes.
I see. Oh.
That's also.
Yeah, that is another possibility.
The edges, but not
Just
the.
want some path to exist.
Yes,
such
yes.
path to exist.
Yes.
This result about edge deletion that you had earlier for a biaxis.
Mhm.
Like, can you, so if I give you a graph, can you figure out what, and maybe a pair of vertices, can you figure out what paths witness this?
I
Is that
think,
computationally?
I think no.
Oh, okay.
You think that that's computationally hard?
Yeah.
So the proof would do something very non-constructive.
Yes. Yeah. So for this, for the vertex version, that is non-separating path, we know that is hard parameterized by K. But on some special class of graphs, we have FPT results. And we were able to show that it's unlikely to have polynomial kernel, even for some special restricted graph classes.
Sorry, now what is K?
K is the path length.
I see.
But contrastingly and interestingly, the edge version of this problem becomes FPT with respect to K. And this is, I would say, that not very common in edge deletion problems, not graph partitioning problem in general. So I know only two of other problems where the vertex version is edge version is FPT. Keyway cut and bisection are those two problems. And here also we don't have polynomial kernel.
So when you say unlikely, what does that mean?
Under certain complexity.
What are the usual complexity?
So it's co-np/p is not p. Sorry. I'm messing up with that dimension.
P to the 2np, you mean?
I'm sorry.
You mean P to the 2np?
I think you need co-np/poly, not np. I mean, poly and np/poly are not the same. I mean, basically your hierarchy doesn't collapse to.
Yeah.
some sort of-
I don't remember what exactly that assumption is. Yeah. But something breaks down here. Yeah. So again, this generalization for this would be like, what if we are given a set of terminals instead of only one set of terminals, one pair of terminals? What can be done? We don't know. This is one direction one can look after. The third problem is purely graph partitioning problem. So this problem, why I am saying it's connectivity and partitioning, because in one part I am maintaining ST connectivity and I want to partition in that way. So I want to partition graph into two parts. So in one part it's maintaining ST connectivity and other part is maintaining in general connectivity of the graph. The constant keyway cut, before constant keyway cut, what's the keyway cut? The keyway cut is basically I want to do a vertex partition by deleting vertex partition into k parts by deleting at most s edges from the graph. So when k equals to 2 and s equals to 2, if I remove these two edges, then I have two parts. One is this vertex, the other is the entire thing.
Wait, you want to penetrate graph 20 here, there will at least two sets. So what are the two sets here?
Yeah, this one and the entire this one.
I see. So there are at least J sets and the number is that one. Okay.
Yeah.
So you want to break the graph into almost a k-partite.
Not
the opposite of K part, right? There are no edges
Not
crossing.
k-partite, whatever it is, k cluster.
Yeah, J clusters.
K
Yeah.
Not even cluster. So there might be examples where each component is a very sparse graph.
Yeah, components.
Yeah.
Yeah,
Okay.
components.
By moving edges.
Yeah. And there is another problem in partitioning, which is F deletion. Here I want to delete S edges from the given graph such that the resultant graph is a member of this family F. So, for example, when f is bipartite and s equals to 2, that means I need to kill all the odd cycles from the graph.
Just two, we can do that.
Mhm.
These two, right? The long ones.
Yes. Yes. If I remove these two, then we have this. But the problem we have studied is basically a hybrid version of these two, where we are given f, k, s, all three. I want to delete s edges from the graph so that I want k components, exactly k components, and each component should be an induced subgraph and a member of f, the given family. Not only I want the members to be the part of those families, the components should form an induced subgraph as well.
You're not allowed to delete edges inside
that. So in the earlier case, if I deleted these two edges, then it was yes answer. But here the thing is, neither we are breaking it into two components, nor this is an induced subgraph. So I have to delete all 5 edges to get rid of those odd cycles. And here we are able to prove one meta theorem which shows that you give me one class of graph for which f deletion enumeration is FPT. F deletion enumeration is basically computation of all inclusion wise minimal solution to f deletion. If I compute that in FPT time, then I can solve our problem in FPT time. Okay. Though tree and bipartite graphs are not in a member of this family where f deletion enumeration can be computed in FPT time, we were able to solve this in FPT time. And when these were all for parameterized by S, the cut set size. When you consider the parameter k, this is para NP hard. That is NP hard for even constant values of k.
So this is all in XP though, right? I mean, you can just iterate over all possible k choices.
Yes.
Okay. What is F deletion enumeration?
F deletion enumeration is F deletion, right? Also, F deletion is given a family. I want to delete some set of edges.
Also, that you get a graph in F.
Graph in F.
Okay, obviously. Okay, fine.
Yeah. And F deletion enumeration is I want to compute all possible solution of certain size. So I want to compute all sets of size at most S, whose removal makes the resultant graph a member of F.
Like you want to delete, you want to understand, you want to find all sets of edges that you can delete so that the graph becomes bipartite. All sets of size at most k that makes the graph.
Oh, I see.
The enumeration problem presumably is just to like write down all solutions.
Yes.
What does it mean for F deletion enumeration to be in FPT? What does it mean for F deletion enumeration to be in FPT?
Yeah, you can enumerate all possible subsets in FPT time. So you can think of graphs with like a constant forbidden structure, cluster graph. If you have an induced P3, you know that the graph is not a cluster graph because
There could be a lot of solutions.
Yeah.
So there could be a lot of solutions.
In particular,
Yeah,
number of-
there could be a lot of solutions.
So what does it mean to say it's an FP? Like the number of solutions is exponentially.
Yeah, it's
that
C to the
also-
power
The number
k.
of solutions
So the
itself
C to
now
the power
has to be at most f of k times poly.
Yeah.
So you're saying you can't have
have
number of
those cases.
solutions also.
Yes.
But then what does it mean for, I mean,
Actually, can you, I mean, you have to have some examples, yeah. Can you, for what are some natural simple classes?
Yeah, that
but
click.
then you're saying a
You can
problem
think
is
of
not
click.
in this
So
class.
initially,
You're saying that
you-
substances are some-
You can't have this structure. Right? So then what you can
Which
do?
structure?
the path on
This
the
structure.
Because the third edge will be there?
Yeah, this edge is missing.
Okay,
So induced P3 can't be there.
okay.
So you know to ensure that the graph, resultant graph is clipped, either you have to delete this edge or both. You know this. So you can basically branch on this. you first delete that edge, right? And check whether the
So
graph
your
is.
goal is to output all solutions of size k? What is your goal?
So if I am given all solution of size, all solution of the affiliation enumeration, then I have one algorithm which can tell me that.
What is that one FPT? There's no S for that one. It's affiliation enumeration, there's no S. S was the parameter of like.
S was the parameter because you are deleting.
Oh, yeah, S just has to be.
Yeah, you are deleting S edges. So for this, so the branch tree, your branch tree will look like this. So for one branch, you have deleted this edge. Now you have one graph. In one branch, you have deleted this edge. You have this graph. So basically, you are branching on this. Right? Okay. So again, you are checking whether there exists an induced P3 or not. If there exists one, then you are guessing which edge do you want to delete. But where do you stop? You know you can delete at most S edges. So the height of the tree is at most S. And each node has degree at most 2. So the possible solution, you will get all the possible solution at the leaf. What is the possible number of leaf with of a tree of height S and degree 2?
It is something that's exponential in the parameter.
Yes. Yes.
Okay.
Okay. So we try to do this, whether we can partition the graph with bounded tree with graphs or planar graphs or unweightable graphs, but we could not do. And other structural parameter is also a point of interest. And the cardinalization direction has not been explored yet. Next, I will move to fair allocation.
So let's say about 10 minutes more.
Okay.
Yeah.
In the fair allocation, what I have a set of items, positive integers, and a set of agents, and I want to maximize the this satisfaction of or the utility value of each agent, such that each agent gets at least the profit value of eta. Right? The goal is clear. But they are
Wait, I was reading it.
You want to maximize the minimum utility. You want to
yes,
ensure that the minimum utility has to be.
Okay,
Yes.
got it.
Yes. But there might be scenarios where you can't assign a pair of items to the same agent because they might have conflicts between them. So how to capture this? This can be captured using a conflict graph. You are given a conflict graph defined on the set of items, right? And what you want to allocate items to the agents in a way that the set of items has utility value at least eta. Not only that, they induce an independent set in the graph.
Okay, because
Because I don't want conflicts between them. So if you look at this, consider this example when a equals to 2 and eta equals to 16, we have this allocation. And these are the utility values for the agents.
okay.
These are forming independent set. But we wanted to capture much more than this. And so before going into that, so this is, can you find the similarity between this and the constraint KY cut, the last problem I have defined? So in the constraint KY cut, I was trying to find a set of edges whose removal the graph into key different component, and each component is a member of given family. If I set the family as independent set, and I change the objective to instead of minimizing the cut set size to maximizing the utility value, then this is exactly the conflict KY cut. So this is where the conflict KY cut comes into the role while studying the fair allocation. And thus, this is the overall picture that partitioning is related to fair allocation as well as constraint KY cut. Okay. So as I was saying earlier, that we want to keep add more constraint. I want to capture more constraints on our problem instance. So think of this scenario. So in university, we want to assign some courses to students, but they have to complete some fixed credit, and each course has some workload or the weekly conduct hour. This course is of this credit, so this much weekly teaching has to be done. And the courses in between might have conflicts between them, depending on maybe one is prerequisite to other, maybe they have overlapping content. Because of these all factors, they might have conflicts between them. And as I said earlier, no two conflicting course can be assigned to one student, but they have to satisfy their required credit, but they cannot exceed their workload limit. So how to capture this? So this is where we define this problem, which is budgeted fair allocation, where instead of like having elements, here we have elements with particular cost. If you want to have this element on your back, then you have to pay this much. And you have a fixed budget. You can buy this element with this much cost, but then you are remaining with this. Right? So this is like clearly more general problem than the earlier one. And this has two variations, complete allocation and partial allocation. In the complete allocation version, what we have is we want to allocate all the elements to agents. And in the partial allocation version, what we want, there can be some elements which are not assigned to any of the agents, because the agents, the utility value that has been satisfied for each agent, so I don't want to allocate more. And each of these version generalizing to different problems. The complete allocation is basically generalization of coloring. I want to partition the graph into independent set with respect to some constraints. So if I can solve this, we can definitely solve the coloring problem. And the partial allocation is solving the generalization of the natural problem, because I have this much budget, I want to maximize my profit. So how do I put those in my knapsack?
But even it is possible that there is no complete allocation, but there is a maximum allocation that you can get.
Yeah, that is possible. That is possible. Then we can deal this with we change the eta. We can vary the value of eta, and we can check whether for this eta the problem instance is a yes instance or not.
Okay.
For which eta I don't get the yes answer, so that -1 is the maximum allocation.
No, not maximum, maximal. I wanted to say that maybe you cannot color all the different items, but you have promised that any item that you don't color, it cannot be assigned to one of the bundles.
Okay, that is another version that is called fair allocation with charity, right? So if I'm not mistaken.
I mean, charity usually doesn't consider these conflict graphs.
Yeah.
Conflict graph setting. So
Yeah.
So imagine, suppose you have a fleet of size 4 and you only have 3 agents.
Yes.
There is no complete allocation,
Right.
but there is a maximum allocation.
Maximum allocation. Yes.
So is it somewhere here, or is there?
No, so we are not capturing the notion of like we are wasting, in a sense, we are wasting the rest of the resource.
You're not wasting it. You cannot assign it. It's just impossible.
Yeah.
it might be possible that a maximal allocation may not, kind of even, no, actually a maximal will.
Maximal will be there.
I mean, like anything which achieves this objective, I guess you could complete it to a maximum allocation.
That is true. That is true. Yes.
Yeah.
So it won't correspond to coloring.
It won't harm.
Yeah. So we are not capturing that notion in our problem. Yeah. So here we have some polynomial time results, we have some FPT results, but what I want to focus is cardinalization, because in the domain of fair allocation, the cardinalization has been studied very less. And this is something I think I would like to do work on. And So for the cardinalization, we have cardinal for this polynomial cardinal parameters, the neighborhood diversity, maximum degree, tree width, but all this for partial allocation. For complete allocation, even if you combine all these parameters, we don't have any luck. So there is scope of like various future work. So this is somehow kind of trying to maximize the minimum value of the one agent. And there is another notion called proportional allocation, where every agent you want like similar kind of utility value. There is EF1, EFX allocations. So that would be interesting. A fair allocation with preference graph. Here we have started with conflict graph, but with preference graph where each agent has some preference or items have some preference over agents. And so here we have captured the conflicts between items with it as a graph, but there are notions of matroid as well. So where the independent set in matroid are those elements which are not non-conflicting. So quite often the conflicts can be is captured using matroid constants. So that is also another notion. If the conflicts is given as matroid, how to deal with that. So do I have time to go over this?
Not a proof.
Okay.
You have 2 minutes. You can decide if.
Okay.
Maybe if you want to introduce one.
Okay, I'm following so far.
Shouldn't that AI? No, it's okay. No.
Yeah, so the overall picture is like this. So we started working on some graph problems, which deals with graph connectivity and graph partitioning. Then there is one problem we have encountered, which basically connects somehow connectivity and partitioning. We move to one partitioning problem, that is this, and then we realized that look, this is quite related to the fair allocation, which falls under like social choice theory also. So this is like you can think of theory to practice kind of overview. Yeah, that is all from my end. Thank you.
Well, somewhere you have mentioned that some problem you can show that there are no polynomial kernel.
Yes.
How does one show this?
Yeah, so it's similar like NP-hard problem. So you W-hard problem. So you know that for this problem there is no polynomial
So
kernel.
that's also a conditional.
Condition.
So I think that is the condition that they otherwise peak would be. Is a condition of the kind that if this one had a polynomial kernel, then finding max least would have kernel or something like that.
Yeah.
What is this class W that people keep talking about? Did they
So
say
it's-
W1, W2?
Yeah, it's analogous to NP hardness in parameterized setting. So for which in classical complexity theoretic setting, what we say that if we don't have any polynomial algorithm, then the problem is NP hard. Here we say that if for some parameter the problem is not FP, then we say that the problem is W hard.
Mean that WK hard.
Yeah.
Okay.
What's in W1 and W2? W1 and W2, what's
So the more greater the I is, the problem becomes more harder.
So what are some examples? Like what is the example?
So example as in
W1 would be max click
is in W1.
parameterized by size.
Yeah, independent set, dominating set, all those are W2 hard.
Okay, independent is W2. Click is in W1.
W1. Because these are not parameter preserving. So in classical
Oh, the N minus.
N minus
Yeah,
K.
vertex cover is everything. No questions.
I have a non-serious question. Why is that bordered twice and the other things are bordered once?
Oh, this one?
Yeah.
So this is of significant importance because this connects to partitioning. That's why
I spent a lot of time thinking about this. I thought maybe this is the one he wants to talk about. Maybe the next
You're
one.
not supposed to.
So in that vein, is the color of the combination of the thing category?
combination of the two.
Okay, sorry, I think that's talking. That's fine.